So the next step, as we did last time, is to pull all of these unknowns, right? The summation and the unknowns out of the integrals. All right, let's do that. So on the left-hand side, we have d dt of, well, let's actually pull the summation out of everything. Let's pull the summation out of everything. So I goes from 1 to n minus 1 ddt. I mean, the only thing, if you look at the whole left-hand side, the only thing that depends on time is what? Okay, so maybe I haven't been very clear. So when you look at the differential equation, right, the differential equation is no longer a function of just the space. The u is now a function of x and t, right? So let me complete. U is a function of x and t. Okay, because we have time and space. So now when we represent this u as a summation of ui times vi of x, just to remember this u is u of x and t. Okay, how about this vi of x? Vi of x is, as I said, these kind of a head functions that we know what they are. If you give me I, I'm going to give you a vix, right? It's not a function of time. So the only function of time here is this ui, instead of being numbers that we can solve as last time we did by solving a matrix equation. These ui's are now functions of time. So this decomposition is essentially kind of a splitting the function being a function of x and t into a summation of the product of functions of just time and functions of just space, right? This kind of a splitting actually is very interesting in not just in numerical PDEs, but in partial differential equations in general. I mean, if even in a lot of the analytic techniques people use to solve and even prove different properties of PDEs, this kind of a decomposition of a function of space-time into the summation of functions of just space and functions of just time is very commonplace. All right. So now when we apply this decomposition into here, we have to remember that ui is a function of t only, and vi is a function of x only. So time derivative, which has to be applied to these ui's, right? Can be, they have to stay in the time derivative, but that can be pulled out of the integral. And the phis have to stay in the integral because they are functions of time. Because they are functions of space, sorry. So vj, vi, dx. So that is going to be my entire left-hand side. My right-hand side is going to be minus kappa times, again, we pull the summation. Computer very slow for some reason. Summation n minus 1 of ui times this integral d phi j dx d phi I dx. Okay. Okay. So this entry is what we have been calling. We have been formed into a matrix last time, right? So we called this Aij. Okay. And by the way, this matrix, if you look at into finite element literature, is usually called the stiffness matrix, just because if you look into, if you use finite elements to solve structural problems, this term it usually comes from the stiffness of the materials. So it's just a kind of a technical term due to historical reasons of the application, one of the first applications of finite elements. Okay, and then we have this right-hand side that's basically copied down. And this is something we formed into a right-hand side because this term does not involve the unknowns, right? This is what we called the BJ previously. Now, let's look at this equation. The entire right-hand side is nothing new, right? We have done exactly the same thing, except for previously we set the right-hand side to 0. So the first term removed of the negative sign is equal to the second term. And we solve this matrix equation to get the unknowns. Now today, we have something additional. We have time derivative of the unknowns, u as a function of time. No surprise here, right? What is surprising is this guy. The integral of the product of pairs of our basis functions, Vj times Vi. This is another matrix because for every I and every j, it has a number. And this is something we usually denote as Mij. Again, in finite elements literature, this matrix is called a mass matrix. Again, because of in structural dynamics, this term usually came from the mass or inertia of the materials, right? So essentially, what we derived is a equation that is the summation of I of Mij times not ui, but the time derivative is dui dt is equal to, again, a summation over I of my stiffness matrix. I mean, I use A here, but in a lot of finite element literature, they use K for the stiffness matrix. Ij times ui here, and plus Bj, right? So that's well, I think we have a minus kappa multiplied here. So essentially we have derived something like this.